Welcome back, students. We are going to continue now with our discussions. So previously we talked about dielectrics. We said when we subject a dielectric material, which is an insulator, to an electric field, then you would have an equivalent of accumulation of positive charges on the one side and negative charges on the other side, because there is no such accumulation per se, because so unlike conductors, there are no free electrons in dielectrics which will move due to an external field. But as I keep saying, because of the presence of an electric field, there will be a stretching effect that will happen in the case of dielectrics, and because they stretch inside the substance, it's the stretching of molecules inside the substance, their positive charge center and negative charge centers are separated, and they result in a dipole moment, and effectively the inside ones will cancel because they will be very close to each other. So outside we will have positive on the one side and negative on the other side. So this is what we saw in the case of dielectrics. Okay. And we also talked about capacitors, and we said a capacitor is simply two conductors separated by an insulator. Okay. The insulator can be a vacuum too. Okay. And we also derived an expression for capacitance, and then we said capacitance is something that is dependent entirely on the geometry of the capacitor. It does not depend on the material, it has nothing to do with the materials, whether I use gold or aluminum or iron or whatever. If I have a certain arrangement, like if I have two parallel plate capacitor, if I have two parallel plates which make a capacitor, then the capacitance is going to be equal to epsilon naught into A by D, the area of either plate and the distance between the two plates. So that's what we saw in the previous videos. In this video, we are going to start our discussions by combining these two ideas. So you have a capacitor, and we derived the expression for capacitance for vacuum, and now if I keep a dielectric substance between the capacitors, because that's also an insulator, right? So what is a capacitor? Two conductors separated by an insulator. So I'm going to put a dielectric substance in between the two metal plates, and let us see what is going to happen because of this. What happens to capacitance, and why is this important in the scheme of things? Okay? So we'll start with it now. Okay. So I have two parallel plates. Okay. They may have charge Q, and charge Q, and plus charge Q here, and minus charge Q here. Okay. And this will also result in a surface charge density. So that is sigma plus sigma, and this is minus sigma. Okay. And then there is an area for each plate. So this is area. So you have area A here, you have area A here, and then there is also a distance of separation. Let's say A. This also have A here, and then there is this distance of separation between the two plates, which is D. And we said this. So E outside is going to be equal to 0, and E outside is equal to 0 here too, and E inside the two plates, okay, this positive is like negative, E inside is going to be equal to sigma by epsilon naught. So each plate will have sigma by 2 epsilon naught as the field strength, and the direction of the field of each plate will be the same, so they will add up to produce this one. Sigma E is equal to sigma by epsilon naught. So we know this, and it also gives you the potential difference, right? So what is the potential across the plates? V is equal to E into D, and that was equal to sigma epsilon naught to D. And this resulted in the calculation of capacitance. Capacitance was simply set Q by V. It's like this. For a given voltage, how much charge can this capacitor hold? So for a given voltage, how much charge can the capacitor hold? And that is the capacitance. So when I do that, when I manipulate this equation, I take instead of Q, I take sigma A, and then for V, I take this sigma D, and then epsilon naught will go up. So sigma will cancel, then I got this expression, epsilon naught A by D as a capacitance. So this is what we did in the previous video. Okay. Now what I'm going to do is I'm going to have a dielectric material between these two plates. Let's see what's going to happen. Okay. First, I have the two plates. Okay, this is positive sigma, this is negative sigma. Okay. Now I'm going to introduce a dielectric material. Maybe I use a different color here. I'm going to introduce a dielectric material. So what will happen? So if this is positive, the plate is, we're going to have positive charges here, then you're going to have negative charges here. So what is going to happen to the dielectric material? Clearly, you will have negative charges here. I know, quite a few. And you will have positive charges here. Okay? Something like that. 6 positive charges here. So, as I said, like at this point inside, E was sigma by epsilon naught. But now, if you take a point, the same point between the two plates, now this time it's going to be inside the dielectric material. So, if you take this point, what would be that E? So, that E would be the combination of the E due to the metal, the conducting plates, and then also E due to these charges, the net charges that have accumulated on either side of the dielectric material, right? So, if I have a positive charge here, what will the conducting plates do? Well, this will push here and this will pull here, so you will have, I'll say E naught. Okay, I'll call this E naught. It's better, right? The E naught. Okay, that's better. So E naught is the field due to the charges on the plates. Okay. Now, what will they do? These things will do. The dielectric material will do. With this positive charge, the negative charges here will pull that in this direction, and the positive charges here will push this charge in this direction. So you will have something like this. Okay, I will call this is ED. Okay, the electric field due to the dielectric substance. So my E is actually going to be E naught minus E. Okay, you see, now E at this point is going to be of a smaller value than E at this point. Okay, so what else do you know? You know that E naught is proportional to sigma. E naught is going to be proportional to sigma. right? The E naught is equal to sigma by epsilon naught. Okay. So what about ET? Okay. ET will also be proportional to the sigma of the dielectric material, right? Because you see, once the negative charge accumulates here and the positive charge accumulates there, then they themselves act as, the dielectric material itself acts as the surfaces of the dielectric material acts as infinite plane, right? You just take this surface alone. So it will also follow the same equation here. But then the strength of the field will depend on the charge density of the dielectric material. Right? I hope you are able to see this. Just like the metal plates, the conducting plates, you have the dielectric substance like this. Okay? Let's say the dielectric substance is like this. This is the dielectric substance you got. But the surface of the dielectric substance will have the charges induced, so now this will act as a plane. And the moment you talk about infinite plane, then this expression should hold good. The expression of E is equal to sigma by 2 epsilon naught that we derived in the first lesson, that should hold good for that also. So this ED, let's take ED should be equal to sigma D. I'll call sigma D as the surface charge density, negative sigma D, and this will be plus sigma D. The surface charge density of the charge is on the dielectric substance. Okay. So that's obvious. And what? Okay, you can go write it clearly. So what is my ED going to be? ED is going to be sigma by sigma D by 2 epsilon naught, again plus sigma D by 2 epsilon naught. They'll add it, right? Okay, so this will give you sigma D by epsilon naught, just like it happened in the case of the metal conductors on top. There it was simply E was sigma by epsilon naught, but here ED would be equal to sigma D by epsilon naught. So I can probably write it here, right? So ED is equal to sigma D by epsilon naught. E naught is equal to sigma by epsilon naught, as you saw there. Then E, the net field, is equal to E naught minus ED. Okay? But you can see that in both equations you can see that A naught is proportional to sigma, and ED is proportional to sigma D. Okay? So now they are opposing each other. So I can then what is my E here? My E can be written as E naught minus ED, which is sigma by epsilon naught minus sigma D by epsilon naught. Then I can say sigma minus sigma D by epsilon naught. Okay? This I got. Well, one more thing. What kind of dielectric substance are we dealing with? We said we would be dealing with the linear isotropic dielectrics only, meaning the polarization will be proportional to the applied field. Okay. So the polarization is proportional to the applied field, then the surface charge density should be proportional to the applied field. Correct? Hope you understand that part. In the case of linear isotropic dielectrics, the polarization of the substance is proportional to the electric field. We discussed that. If we increase electric field by twofold, then the polarization will also increase by twofold, meaning that the net charge on the surface would be doubled. Okay, so I can say that sigma D is proportional to E naught, because that is the main field, right? Why do charges accumulate here? It's because like you have a field here. The field is first set up by the plates. So the plates set up a field in that space. So now you bring a dielectric material, and because you brought the dielectric material there, then the molecules of that dielectric material get polarized. Okay, so the polarization depends on the charges on the conductor. They are the cause of this polarization. So the polarization is related to the charge on the surface clearly, and that must be proportional to epsilon naught. If that is going to be proportional to epsilon naught, then I can say that sigma D is also proportional to sigma. Why? The reason why sigma D is proportional to sigma is because of this. Epsilon naught is proportional to sigma, so sigma D must be proportional to sigma. Hope this is clear to you. Okay, once this is understood, then we can proceed. So, if sigma D is proportional to sigma, then I can introduce a constant right there. I will say sigma D is equal to some constant k into sigma. Okay. But this constant, say the k which is used in your textbook is different from this k. I will come to that later. But understand that the sigma D, it can be expressed like this. Sigma D is equal to some constant k into sigma, because sigma D is proportional to sigma. Why? Because sigma D is proportional to the applied field, and the applied field is proportional to sigma. So sigma D will in turn be proportional to sigma, and that results in sigma D being equal to some constant into sigma. Okay? So once I get this, this results in what happens to this equation? E. So now E is equal to sigma minus k sigma instead of sigma D, so divided by epsilon naught. So I can write it as 1 minus k into sigma by epsilon naught. Okay. This k will be a fraction. This k has to be less than 1 in this case. Okay. Why? Because when k is equal to 1, then 1 minus 1 will become 0. That can happen only in the case of the conductor. So only in the case of the conductor can the field inside become 0. But if you take a dielectric substance, the field inside cannot become 0. It can only be reduced from the original value, like this. This field is going to be smaller than this field. Okay. So this can never be equal to 1. It has to be less than 1, so that we get a reduced E. It's not sigma by epsilon naught, but it's going to be 1 minus some number which is less than 1. So sigma by epsilon naught. So we get a fraction of sigma by epsilon naught. So this E is going to be less than epsilon naught, which means that this k must be less than 1. Okay, in this case. So I can also write this as 1 minus k can be written as something else. Okay, this I'm going to write as, I got epsilon naught here, right? So I'm going to have something else there. So I want to write this as sigma by epsilon naught, and now that I have brought this substance here, I'm going to write this as sigma epsilon r. Sorry. This is permittivity of free space, and I'm going to write this as the relative permittivity. Okay. So what does it mean? Which means that 1 by R is equal to 1 minus K. So the relative permeability epsilon R is equal to 1 by 1 minus K. Okay. Right? So notice here, I said this K must be a fraction. So this 1 minus that fraction will be less than 1. But 1 by that fraction will give you this number epsilon R, which is greater than 1. Okay? This epsilon, this results in epsilon R being greater than 1. Okay? It's a very important result. And I call this epsilon R as relative permittivity. This is permittivity of free space. Now I got a dielectric substance here. Because I have dielectric substance here, I have a new number, a constant, epsilon R. I'm going to call this relative permittivity. This is permittivity of free space and this is relative permittivity. In your textbook, this is not given as epsilon R, but this is given as K, called as the dielectric constant. Relative permittivity or dielectric constant. Okay, that will be greater than 1. In your textbook, this is K, not this K. Okay, I have used this K as a temporary constant to get to this point. This is important, this is not important. Okay, I am going to write this number as 1 by epsilon R. Epsilon R will be greater than 1, so 1 by that number would give me a fraction which will anyway be equal to this 1 minus K. That is what we got here. Okay, if you understand this, then we will continue. Notice that here, when you didn't have the dielectric, epsilon naught, the field between the two plates of the conductor was sigma by epsilon naught. But because you have the dielectric substance between the two plates, now the same E has become equal to sigma by epsilon naught into epsilon R. This is a number which is greater than 1, so E will be a smaller number than this E naught, because you take E naught and you are dividing it by epsilon R. I can also write it as epsilon naught by relative permeability. Sigma by epsilon naught is actually E naught. So this is equal to epsilon naught by the dielectric constant. In your textbook says it is E naught by K. Your textbook uses the symbol K for this number, but I am using epsilon R because epsilon, it's going to be used along with this epsilon naught, right? So I am using this epsilon R. In your textbook, it is called as K, and this number is greater than 1. Okay, so once we understand this, then we will go ahead and then do the rest of the derivation. Okay, so we said E is equal to E naught by epsilon R. So that's a field between the two plates of the conductor. Now, what would be the potential difference? So this is a constant. So the potential difference between the two plates now will be this E into the distance D. The same distance, right? The same plate, the same arrangement, except that you have inserted a dielectric material in this case, right? So what would be the voltage here? So voltage with the dielectric dd is equal to E into D, that is going to be equal to E naught D by epsilon R, but E naught, you know, this sigma by epsilon naught epsilon R and sigma D. So that's the voltage now across this. What is the voltage here? It was simply sigma d by epsilon naught before. But now notice it is sigma d by epsilon naught into epsilon r. So the whole thing is divided by this thing, epsilon r. So voltage also reduces. For the same charge density, if you have charge density sigma here, if you have charge density sigma here, for the same charge density, here the field is greater, here the field is smaller by this amount. Okay, and this is called as a dielectric constant. I keep talking about it now. Okay, so then what is the capacitance now? So we know that the capacitance is equal to Q by Vd. Again, what is Q? Q is the same, sigma into A, because that's the charge on the plate, right? That's charge density on the plate. So the charge density on the plate is sigma in both cases. Okay, so this is going to be sigma A, so divided by what is Vd? Sigma d by epsilon naught epsilon r. So I'm going to have epsilon naught epsilon r here. So this and this will cancel. So my capacitance is now equal to epsilon naught epsilon r A by d. Okay. So notice that epsilon naught A by d is the original capacitance. I'll call this as C naught. Okay, I'll also call this C naught here. C naught. Now C is actually equal to epsilon r into C naught. So you see the capacitance has increased because of this. Previously we had just C naught, and this is a number greater than 1. So the capacitance of this arrangement has increased by this factor, the relative permittivity or the dielectric constant. So by introducing a dielectric material between the two plates, we have increased the capacitance of the capacitor. So the capacitor can hold more charges for the same voltage. Okay, I hope you understand this. Okay, so the effect of a dielectric substance used in a capacitor is to increase the capacitance of the capacitor. If the dielectric substance is not present, the two metal plates will have a certain capacitance based on their area and then the distance of separation between them. But if you introduce a dielectric material between the two plates, then the capacitance increases by a factor of the dielectric constant or the relative permittivity. Okay? So let's do a problem and then see how things work out. I'm going to do example problem 2.8. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, but has a thickness 3/4 of D, where D is the separation of the plates. How is the capacitance changed when the slab is inserted between the plates? Okay. It's like this. Okay, let's go through the problem again. A slab of material of dielectric constant K has the same area as the plates of a parallel plate capacitor, but has a thickness 3/4 D, where D is a separation of the plates. How is the capacitance changed when the slab is inserted between the plates? So you have the plates here. So they will have an area A, right? Okay, an area A, and the same area will be here too. And now you are inserting a dielectric material. And actually the distance of separation is d, but then the dielectric material is only, I will use different color. It is only 3/4. Okay. So the question is, what would be the effective capacitance? And this dielectric material is only 3/4, right? Okay. It is 3/4. So how do we find the capacitance? Well, the capacitance now is actually equal to Q by V, the potential between the two plates, right? Okay. Now let's see what the potential between the two plates is going to be. Let's see what is going to be E in this space. It's going to be, suppose I have surface charge density sigma, and this is going to be minus sigma. So the charge will be actually Q plus Q is on this sigma into A, right? And this will be minus sigma into A. That's on the other side. And now we will have negative charges accumulating here. How much you don't know. Okay. But what is this going to be? This, the field here in this space, I'll call this as E1, and then this is going to be E2. Okay, but what is E1? E1 is going to be equal to, because there is no dielectric material here, so there the field value is simply sigma by epsilon naught. We know that. And what is E2? Within this space, the field is going to be reduced, right? So that would be, we know it is going to be this E1 by K, right? They said the dielectric constant is K. Here, epsilon r is actually equal to K. They said the dielectric constant is given by the symbol K. So what is E2? E2 here is going to be sigma by epsilon naught into epsilon r, and is actually K. So that is actually equal to E1 by K. So we've done that already. So the field here will be a reduced field, and this will be the regular field, E1. So we got this. Now with these two things, I need to find the potential difference between the two plates. So what is the potential difference between this point and this point, and this point and this point? V is equal, the potential difference between the two plates is going to be equal to the potential difference in the free space plus the potential difference within the dielectric. Right? This potential difference plus this potential difference. So what is that potential difference? It is simply E1 into, if this is 3/4 by D, this will be D by 4, right? So this thickness will be D by 4. So that is actually E1 into D by 4 plus this would be E2 into 3D by 4, this thickness. So can we do it now? So E1 is going to be sigma by epsilon naught into d by 4 plus this is actually sigma by epsilon naught k into 3d by 4. So what are the things that you can take out? Common, you take sigma out and you can take d out and you can also take epsilon naught out and 4 to epsilon naught. I can take that. So that leaves me with what? 1. Here it's going to be 1 sigma naught d1 plus 3 by k. This 3k. Sigma d epsilon naught 4 if I take out, and that leaves me with 3 by k, and here 1. So 1 plus 3 by k. So the voltage is actually equal to sigma d by 4 epsilon naught into k plus 3 by k. That's the voltage between the two plates. Now what's the charge? Charge is simply Q is equal to sigma A, right? So the charge is simply sigma into A. That's the charge on the plate. So the capacitance is equal to Q by B, that is sigma A divided by sigma D to k plus 3 by k, and then 4 epsilon naught will go up. Sigma and sigma will cancel. So what are we going to have now? We are going to have sigma naught A by D into this 4 divided by k plus 3 by k, that k will go there. So the new capacitance is equal to sigma naught A by D into 4k by k plus 3. Okay, and this is also equal to what is sigma naught A by D? That is, if I didn't have this capacitor, the dielectric material inside, then the capacitance would have been epsilon naught A by D. That's my C naught, right? Okay, I'll say if you take my C naught, then what will happen? It is sigma naught A by D. So this I can write as sigma naught, C naught into 4 k by k plus 3. Okay. So C is equal to C naught into 4 k plus 3. We also said the dielectric constant K, the dielectric constant is greater than 1. Suppose it was 1, suppose it was 1. So this term would become 4 by 1 plus 3, 4, this will become 1. Okay, but now we said it is greater than 1. So suppose it is 2, let's say k is 2. Then what would you get here? 4 into 2, 8, divided by 2 plus 3, 5. So 8 by 5, it will be greater than 1. You see, the capacitance will be greater than the previous capacitance without the dielectric. So by inserting a dielectric, either covering the space fully or partially, you are going to increase the capacitance. If you have covered it fully, then you would have increased the capacitance even more, But since you have covered the space only partially, you are going to have a slightly less capacitance, but even then, that the new capacitance will always be greater than the old capacitance without the dielectric material. So you can clearly see that the introduction of a dielectric substance results in increased capacitance. So let me ask you this question. Without the dielectric substance, the only way you can increase the capacitance of a capacitor is either by increasing the area or decreasing the distance of separation between the plates. But if you're going to use a dielectric substance, you don't have to increase the area of the the plates. You can have the same area, and you don't have to reduce the distance. I mean, you don't want to do that, because if you bring it too close, they even touch, and then the whole idea of capacitance will go for a toss, because the moment they touch, then they become conductors. So there is a limit to how close you can bring two plates, right? So without reducing the distance of separation between the two plates any further, the introduction of a dielectric material automatically increases the capacitance. So that is the importance of dielectric substance. Okay? The reason why you study the nature of dielectric substance is this. Now you can understand the introduction of a dielectric substance is very useful in increasing the capacitance of a capacitor. So if you want to hold more charges for a particular voltage, then all you need is to introduce a suitable dielectric substance between the two plates of the capacitor. Then your requirements will be met. Okay? So that is why you studied about dielectric substances. The dielectric substances are very, very, very useful when you are building capacitors. Hope this is clear to you.